So hello students, welcome back. See, here is the question from binomial, the series of binomial, the double summation. See, if though you people have are continuously following our channel, then you would have definitely got the idea how to solve it. Today again I am going to use our matrix method, which I have discussed in detail in I think 2-3 videos back on the question based on binomial theorem only. Okay. So I'm going to use that method here. So what's the method? I will say, okay, let's complete the matrix. So I will like to form a matrix here. So matrix will be something like this. So along the row I'll be writing ICI, and along the column I'll be writing ICJ. Okay. So that means this is one, and of course when I'm writing CI, that means NCI. Okay, that's for sure. So I into NCI. So I 1 into C1, 2 into C2, 3 into C3, and so on, N into Cn. Similarly, along the column also I'll be writing 1 C1, 2 into C2, 3 into C3, dot, N into Cn. Now let's try to complete this matrix and see the pattern. Fine. So I will request you all, if this is something new for someone, to go back and watch the video in which I have discussed this thing in detail. That was a video where we have solved the double summation of 1. Okay. Now here, so the first entry will be 1C1 into 1C1 here. So it will be 1 square C1 square, and then it will be 1 into 2 NC1 into NC2. Okay, this will be 1 into 3 NC1 into NC3. Likewise 1 into 4 dot, and this is 1 C1 into NCN bacho, N into Cn. Okay, similarly this will be 1 C1 into 2 C2, and this will be 2 C2 whole square, and this will be 3C3 into 2C2, and so on. This will be NCN into 2C2 here, right? 2C2 here. Likewise, you go on writing it. So this will be 3C3, 3 into C3 whole square. Okay, and similarly it will be 3C3 into 1 into C1, and this will be 2C2 into 3C3, and so on. Okay. Now see, if we add all the terms of this matrix, won't we get the sum of this entire series, where entire series means, okay, no, not that the entire series, rather that will be double summation of I into NCI, J into NCJ, where I goes from 0 to N and J goes from 0 to N. That means, what does that mean? That means the sum of all possible such product, okay, where I and J has no correlation, they are totally independent of each other. So this gives us sum of all elements of the matrix. All of you agree to that, bacho? Isn't that? So if we add all the terms, won't we get all possible combination? Answer is yes, we will get. And how can you check it? See, if anyone has any doubt regarding this, so what you can do is just start with, see, I equal to 0, J equal to 0 won't be of any value, because 0 into 0 is 0. Okay, so start with 1. So let's say I assign value to I as 1. Okay, then J will take values from 1 to N. So I am just trying to show you. So put I is equal to 1. How you can verify and justify it? So that means you will get 1 into C1 and then summation over J, and when you open that summation you will get 1 C1 plus 2 C2 plus 3 C3 NCN. That's the first row. Okay, now that's the first row here. Or you can say the first column here is the same thing, 1 C1 So 1C1 whole square, and then 1C1 into 2C2, 1C1 into 3C3, like this. And then similarly, when you put I is equal to 2, you will get the second column, third column, and hence the sum of all the elements is given by this series. And solving this series is really very simple. Why? Because they are independent. So I can simply write it as NCJ, J goes from 1 to N, and this into similarly I into NCI, I goes from 1 to N, isn't that? Now how to just like simply solve it? So we can write I into NCI. So we need to just solve just one here. I goes from 1 to N. So what you can do, you can apply Bahubali property. For that Bahubali property, I will take choice to start from 0. Whether start from 0 or 1 won't make any difference in the series, but in Bahubali property it may be of helpful. Why? Because see, I will be applying Bahubali property, and what it says that if I replace I by N minus I, you remember Bahubali property, that again we have discussed in the previous question. Okay, so what it says, let's say we have R into NCR, R goes from 0 to N, and then if I replace R by N plus 0, the initial value of R, the final value of R minus R. So if I replace R by N minus R, wherever you have R, the value remains same, bachon. So this is S, this is S. Okay. So applying Bahubali property, you get N minus I, NCI, because NCR is same as NC, N minus R, and that's the summation. So add them after applying Bahubali property. Normally we add the statement which we have, which we are given, and which we get after applying Bahubali property. So 2S is when you add them, I into NCI, I into NCI get cancelled. So summation N into NCI. So I goes from 1 to N. So that is nothing but you take N common here. Okay, and then this is I goes from 0 to rather it's 0 to N. So this is nothing but it's 0, right? I goes from 0 to N. So N you get out of it, you are left with NCI, and this is nothing but 2 raised to the power N. Therefore S is N into 2 raised to the power N minus 1. So that's the summation for this one. So this is nothing but, so this series, rather the sum of all the elements of matrix is given by N square into 2 raised to the power N minus 1 whole square. So N square into 2 raised to the power 2N minus 2. That's the sum of all elements of the matrix. Okay, coming back to this part, there's one more method to solve this series. Let me discuss it, and that method is that, see, we have to solve for I, NCI, you can write it as N factorial over I factorial into N minus I factorial. Okay, you cancel it, you have I minus 1 factorial. Now in this method, this holds the key. You shouldn't change N minus I. Whatever term you have here, you shouldn't change it. Okay, I goes from 1 to N, because here I goes from 0 to N or 1 to N won't make any difference. Okay, so this is I goes from 1 to N. Now I will manage it. Okay, so I will write N factorial as this. So it's I minus 1 factorial into N minus I factorial. Now since I is common, N is a constant, you can take it out of the summation sign, because the variable of summation is I here. And then you can write it as N minus 1 C I minus 1. I goes from 1 to N, and this is sum of all binomial coefficient. Why? Because I starts with 1. So when you put I is 1, you get C naught, and when you put I, replace I by N, you get the last binomial coefficient C N minus 1. So this is nothing but sum of all the binomial coefficient, hence this is equal to this thing. Okay, so we saw Bahubali property, we saw the general term method, and now we are discussing the matrix method. So anyways, now coming back to it, now see, the series which we have to solve is where I is less than j, which is on the other hand less than equal to 1 and greater than equal to 0. So whatever it is, that remains same, I less than j. Okay, so in the matrix, of course, that's the diagonal element where I is equal to j. So along diagonal I is equal to j. So of course on one side of diagonal I will be greater than j, on the other side I will be less than j, bachcho. So as we can see here, below this diagonal all the elements are those for which I is less than j here. For which I is less than j here. So according to this like question, what do we need? So the sum of, or the value of this series is sum of all elements of the matrix which lie below the diagonal elements, which lie below the diagonal elements, bachcho. Okay, so which lie below the diagonal elements. So we have to just get the sum of all those elements which lie below the diagonal element. But by symmetry, of course, by symmetry, see the term you have here, the term you have here, the term you have here, the term you have here. Okay, the term you will be having here will be the same as you have here. So that means by symmetry we can say the terms which are above the diagonal elements are same as the terms which are below the diagonal elements. Okay, so I can write it as this is equal to what? So this is equal to sum of all elements of matrix minus sum of all diagonal elements, okay, and then whole divided by 2. Why? Because if you add all the elements, which we have already done, remove the diagonal elements, you are left with terms above the diagonal elements, term below the diagonal. Okay, and since both the terms are same, so half of it will give you either of them, this one or that one. The answer is going to be the same here. So what next do we need to find? We just need to find sum of all diagonal elements. Now what are diagonal elements? Diagonal elements are, so this is nothing but, so sum of all diagonal elements. If I write here sum of diagonal elements of the matrix, bachcho, is equal to summation I goes from 1 to n, I into nci whole square. And we know, we have already seen in the general term method, where it is here, that we can simplify I into nci as n times summation of n minus 1 ci minus 1. Okay, so therefore sum of diagonal elements, so how much is it? So sum of diagonal elements will be, again I am writing I into nci whole square, so which we can simplify as n square into n minus 1 ci minus 1 whole square. I goes from 1 to n. Okay, so this is nothing but n square into n minus 1 ci minus 1 whole square. I goes from 1 to n here. Okay, now how to get this? See, in one question we are using so many things. Okay, now how to get series of this type? So for that, see, again if I write that series as p, so it is nothing but n minus 1 ci, so c naught whole square, n minus 1 c naught, okay, whole square. I will be replacing it with n minus 1. n minus 1 cr is same as n minus 1 cr minus whatever, n minus 1 minus r. Okay, similarly for I is equal to 2, n minus 1 c1 into n minus 1 c, n minus 1 minus 1, which is n minus 2, plus when you put I is equal to 3 here, so n minus 1 c2 into whole square. So another next one, n minus 1 c2, I will be writing it as n minus 1 c, n minus 1 minus 2, n minus 3, and so on till the last term. Now we already know how to get this value, and what is it? We get this value if the statement is if in every term the sum of subscript is same. So in every term the sum of subscript is n minus 1, you add them, n minus 1, you add them, n minus 1. Then, and you have all possible terms. So we have all possible terms because r is, I goes from 1. So the minimum, like the smallest value of the subscript is 0 and the largest can't exceed n minus 1. So you have all possible terms. Then the sum is given by sum of superscript 2n minus 2, C, the sum of subscript which is n minus 1 for all the terms. So that's it. So this is nothing but, so the sum here is n square into 2n minus 2 Cn minus 1. Now just put these values. So this is for the diagonal elements and this is for the elements here, n square, all the elements. So the answer is finally, so the answer is half times n square into 2 raised to the power, what is that, 2n minus 2 minus n square 2n minus 2 Cn minus 1. So if you want to simplify, you can take n square by 2 common, 2 raised to the power 2n minus 2 minus 2n minus 2 Cn minus 1. I believe, I wish, I hope that all of you would have understood this method very properly. So we use several main things, most importantly the matrix method. So that was second question based on matrix method. I now believe that you all would have properly understood how to apply the matrix method. Rest we use so many things. We use Bahubali property here, here general term method, and how to solve such type of series. Okay, now that the series which appear as product of two binomial coefficient. Okay, so that's it for today, bachcho.